Hello students, so welcome to this video on finding out an expression for effectiveness for parallel flow heat exchanger. So you have seen this diagram when we derived the expression for LMTD method for parallel flow heat exchanger. So this is a parallel flow heat exchanger graph. So the hot fluid is entering at TH1, going out at TH2, cold fluid is entering at TC1, it is going out at TC2. So we know the temperature difference dth that is suppose say if you want to write it now, let us try to find out the expression. Now the differential heat transfer, so that is dq is equal to what? Already it is u times, so we have considered a small differential area dA here. Okay, small differential area dA. So in this small differential area the heat is transferring from the hot fluid to the cold fluid, correct? So it is u dA times, what is that? Th minus Tc. Some temperature here, hot fluid, the heat is transferring from the hot fluid to the cold fluid. Some temperature, some don't know what is the temperature here, Th. So we have given it as Th minus Tc. So always heat is transferred from high temperature to low temperature. Now this is also equal to what? Since the heat is being lost by the hot fluid, which is equal to minus m dot h Cph times, what is that? dTh. Do you agree with me here? The hot temperature is decreasing its temperature along this this slope. So it is dTh, since it's, which is also equal to what? M dot C, heat gained by the cold fluid. So M dot C Cpc times dTc. Is it right? Okay. Now which can be written as what? This can be written as minus capital CH dTh, which is also equal to capital CC dTc, which is I am writing in terms of heat capacity. That is m dot h into Cph is capital C. Similarly for the cold fluid. Now, so if you try to equate it with this, so what is that we are going to end up with? So we are going to end up with dTh is equal to, so dTh is equal to minus dq divided by ch. Yes or no? Ch and dq dtc equal to dq divided by cc. Correct? Now if you try to do the subtraction of these two things, so what is that you are going to end up with? D of th minus tc is equal to d of th minus tc is equal to minus, so th is already minus is there, dq of 1 by ch plus 1 by cc. Yes or no? So this is what the case is. This is the king. So let us call this as equation 1. Now let us try to do some simplification here, substituting for dq. So I am keeping it here, just for your reference I am keeping it here. So substituting for dq, expression 1 becomes so if you try to substitute for dq, expression 1 will be what? So d of, so I am writing it in a little bit arranged manner. So I am going to take the dq this side. So what will be dq? U into dA. So I am going to write only this th minus tc here. I am going to retain that minus ua there itself into 1 by ch plus 1 by cc. Yes or no? Do you agree with me? So this is what the case is all about. So it is something like d theta by theta is equal to something like this. So upon integration, so call this as equation 2. Upon integration, we get. Are you getting it here? It is something like d theta by theta. D theta by theta is equal to something you are having. So if you try to integrate it, what is that you are going to end up with? Ln of theta, correct? You're going to end up with ln of theta 1 to theta 2, something like that you're going to end up with. So between 1 to 2, if you try to do it, so this will not be dA, sorry, this is dA. Now what is it you're going to end up with? Between 1 to 2 area, and between 0 to A here, between inlet to outlet, if you try to do upon integration between inlet and outlet, between 1 to 2, we get, what is it you're going to get? We are going to end up with ln of TH2 minus TC2 minus TC2 divided by TH1 minus TC1. TH1 minus TC1, which is equal to minus UA. It is going to become minus UA into, this will be same na, 1 by CH plus 1 by CC, correct? So this is what the case is all about. Now if you try to take now here I am going to take CH as the common factor, so which is going to, what is that I am going to end up with? TH2 minus TC2 UA by CH. If I try to take it as, purposefully I am going to take it as CH. So what is that I am going to end up with? If I take the CH in the denominator as, so it is 1 plus correct. Now I'm going to keep like this. So TH2 minus TC2 divided by TH1 minus TC1, which is equal to exponential minus UA by CH. So you put a bracket here, this into 1 plus, correct appa? This is what it is going to be. Now then, so please call this as equation 3. Please call this as equation 3. Now what is our goal is, somehow you can see the RHS, slowly I am making it like, independent of temperatures. The left side is still a temperature. Somehow we need to bring in some sort of non-dimensionless parameters other than temperatures. So we will take the help of effectiveness. So in the previous lecture I have defined what is effectiveness. So if you could remember what is effectiveness, so our effectiveness is what? C minimum times TH1 minus TC1. Yes or no? So it is either if you see here, it is Q max, your epsilon will be equal to, yeah, sorry. So your epsilon will be equal to what? CH into TH1 minus TC2, TH2 divided by C minimum. So similarly, CC into this thing. Okay. So we'll take the help of this effectiveness and see that what can be done. We have to bring in some sort of effectiveness concept here. So we know that, I'm going to write it now. We know that, so you should know that before writing this sentence, we know that, correct? So epsilon is equal to CH times, so write it, TH1 minus TH2 divided by, say, C minimum. So please write that TH1 minus TC1, which is equal to CC times TC2 minus TC1 divided by C minimum times TH1 minus, right, appa? Now please try to write this thing. What is that I am going to do it now is I want to write in terms of TH2. So therefore my TH2 will be equal to, just I am simplifying this. So TH2 will be equal to TH1 minus epsilon times C minimum into TH1 minus TC1 divided by CH. Correct? So I'm just rearranging it also. So what is TC2? TC2 is equal to TC1 plus epsilon times C minimum into TH1 minus TC1 divided by CC. Okay, so call this as equation 4 and equation 5. Now if you see here, please observe this. So what is that we are trying to do? So you just see equation 3 where we have TH2 minus TC2 is equal to exponential of this term. When we have written some expression, that is TH2 equal to TH1 minus epsilon C minimum times this. So upon substituting equation 4 and 5, so this is 4 and this is 5 in 3. So please substitute. Upon substituting equation 4 and 5 in 3, we get, what is that we are going to get? Tell me. So I'm going to do one step and finally I'm going to write the answer. Okay, so you please see that. So you see here TH2 is equal to this, right? So in place of that I am writing it here. So TH1 minus TC1 will be common. So let us try to write that here below. 1 divided by TH1 minus TC1 into bracket open TH1 minus TC1 minus epsilon times C minimum into TH1 minus TC1 into what? 1 by CH plus 1 by CC, which is equal to the term exponential of minus UA by CH times 1 plus CH by, correct? Now again, what is that you can do? You can take the common factor. So basically what is that I have done? I have just substituted for TH2 and TC1. Okay, so basically if you see here CHCC, so that comes out here, epsilon C minimum is there. So you can take the common factor TH1 minus TC1 here and this get cancelled out. So finally you are going to end up with this. So therefore you are going to end up with epsilon equal to 1 minus exp of minus UA by CH into 1 plus CH by CC So this goes inside that exponential term divided by, you're going to end up with C minimum of 1 by CH plus 1 by CC. Alvarapa. So this is what you're going to end up with. So please call this as equation 6. Now see, there are a lot of things which is going to be there. First condition, if CC is greater than CH, then what is going to happen? Then C minimum is equal to what? CH. Yes or no? Then C minimum is equal to CH and C max will be equal to CC. Yes or no? Hence, equation 6 becomes, what is that is going to become? So this expression here, if you try to substitute C minimum is that, and all the other things, if you try to do it, you are going to end up with, please see here, your effectiveness is going to be 1 minus exp of minus UA by CH is now C minimum, so I am going to write it as C minimum, correct? C minimum. So please close this bracket, this into 1 plus CH is C minimum, so C minimum by C max. So close this inside that, divided by C minimum is my CH. Yes or no? C minimum is my CH. So if I try to take that as this thing, common factor or something like that, if you try to do it, I'm going to end up with 1 plus, so take that inside, C minimum by C max. This is the thing if you're going to have, if this first for the first condition you're going to end up with. So on the other hand, if CH is greater than CC, then C minimum will be what? CH. CC. C minimum is CC. Then C max will be equal to CH. Therefore, what will be our effectiveness? So our effectiveness will be equal to 1 minus exp of minus UA by CH, that will be there like that only. So close this bracket into 1 plus C max by C minimum, C max by C minimum divided by 1 plus C minimum by C max. It will be common. 1 plus C minimum by C max. So you are going to end up with this kind of term. Okay. So this is the expressions for the effectiveness. Now if you see here, if you try to arrange these two terms, both will be same, either for CH or CC. Now here, be very careful here. We are going to introduce three terms here in this expression. So commonly we can write it as with these two criteria. So upon rearranging 1 and 2, upon rearranging 1 and 2, we get common equation. What is that common equation? Your epsilon equal to 1 minus exp of minus UA by CH, correct apa, into 1 plus C minimum by C max, close this bracket, this whole divided by this. Now what is that we can do? Now the first term, so your term UA divided by C minimum is equal to, is called as, what is called as number of transfer units, which is a non-dimensionless term, number of transfer units. It is number of transfer units. Okay, next thing, your ratio C minimum by C max is what is called as capacity ratio, is denoted by R, which is called as capacity ratio. And third term epsilon, you know already, it is effectiveness. So the last non-dimensionless is the effectiveness. Also you have one more thing, what is called as flow arrangement. Flow arrangement is a dimensionless parameter. So basically what is that? Therefore in general epsilon will be equal to, if you try to adopt all these things for parallel flow, epsilon for parallel flow will be, so you can group all the terms and try to write it as 1 minus exponent of minus NTU times 1 plus minus 1 plus R. So group this whole divided by R. So 1 minus exponent of minus NTU into 1 plus R. So this will be under the square bracket divided by 1 plus R. So this is for parallel flow. Now the same process you can start from the starting till end. You can do it for the counterflow. Little bit cumbersome will be there for you need to little bit be aware of all the work stuff, which I am not doing it. So for counterflow all the other things are same. For counterflow, which I am not doing the derivation, your epsilon will be equal to 1 minus, which I am writing it here, 1 minus, so please see here, I am writing it here. So epsilon equal to 1 minus exp of minus NTU of 1 minus R, NTU times NTU into 1 minus R. This comes under inside the exponential term divided by one minus R into exponent of minus NTU times 1 minus R. Okay, this is for counterflow, this is for parallel. So the definition of epsilon, R and NTU remains the same. So please do the in a similar way, however how I did for parallel flow, please carry out for counterflow and see that you are getting this expression. Are you able to understand? So this is what the thing is. So for condensers and evaporators, actually for condensers and evaporators, the R will be equal to 0. So you're going to end up with a different sort of expressions actually for condensers and evaporators. So let me just simply write it here. So simply I'm going to conclude this very fast. So for condensers and evaporators, for both counterflow and counterflow and this thing parallel flow heat exchangers, your epsilon will be equal to 1 minus exp of minus ntu. That's it. So this will be the case because in cases such cases are found in condensers and evaporators in which one fluid remains constant, correct? So temperature throughout the exchanger here, like at constant temperature throughout the heat exchanger, so C max will be equal to infinity, and thus R will be equal to 0. So that is the case. So for condensers and evaporators, epsilon will be equal to, so where R equal to 1, it will be a typical regenerators, something like that. Okay, so this is all about the things. So basically you will be having you have to solve some problems on this, which we are going to see it in the next video. Okay, thank you. So please do on your own for the derivation of effectiveness for counterflow heat exchangers. Thank you.